Okay, perfect. Thank you for the introduction. So my area of study is located in Delaware Basin, which forms part of a greater basin called the Permian Basin, which currently is one of the most active areas for oil and gas exploration in North America. So this Delaware Basin that is here is bounded to the east by the Central Basin Platform, then to the north by the Northwest Shelf, to the west and southwest by the Diablo Platform and Marfa Basin. So, and here we have a cross-section where we can see the Delaware Basin, the Central Basin Platform, and Midland Basin. So to give a little of context, after the Midland Basin and Delaware Basin were conformed, the rate of subsidence exceed the rate of silicic and carbonate deposition. So that transformed this into a deep water basin. And into the Delaware Basin, my area of study is located in the Wolfcamp A formation, which is mixed carbonate and silicic deposit. And here is I'm going to present two wells, and one is a vertical well and the other is a slant well. So this is how the vertical pilot well looks like. And in this red box is referring to the area that I'm going to present for this preliminary analysis, which is 50 feet. So in the course, we have seen a lot of hybrid event beds. So even though we haven't done a detailed analysis making a discrimination between the different type of deposits, we have seen all of them, and we are going to follow this model proposed by Hutton, and also from Caval paper, where he presents how a hybrid event bed looks like in the Wolfcamp. We thought that this is a good representation because this is exactly what we see in our core, where we start the vent with a more calcareous composition, and while we move towards the top, the composition becomes more siliceous. So this is a good model that adjusts to our data as well. Regarding the conceptual model, so we are in a deep water system conformed by submarine fans, and based on our facies, we can say that we are in a more distal part of the fan. And a difference to this model is that in our area, we have multiple sources that drives sediments to the basin, and as I mentioned before, are related with the basins and the platform that are surrounding the Delaware Basin. So it would be the Central Basin Platform, the Northwest Shelf, Diablo Platform, and Marfa Basin. Now jumping into the data. So this is the vertical well, and this is the slant well. In green, we can see all the core that we have been provided, and into the whole core, we focus our preliminary analysis in this 50 feet, that is the yellow rectangle. And we select this area in particular because the kind of unique aspect of this data set is that we have two wells that are really close one to each other, being this one, the slant well. So we selected this area where the distance between them are less than 150 meters. So here we have, to the left, we have the resistivity, where in red we can see mostly the sands, and then we can see at the top and at the bottom more calcareous or mud rocks rich areas. And this is how the whole 54 feet from the core looks like. We can see the gamma ray here. Here we have the CT scan, which measures the density of the rock. So the color will change regarding the density. That gives us an idea of, we can link that with mineralogy and also with composition. Here we have core pictures for this 54 feet. And then we have the resistivity and some examples of how the XRF data looks like. Here we have the silica, calcium, and aluminium. And from here, we can really see some trends. For instance, if we took a look in this area where we have this red color becoming more yellow and green, it makes a really good correlation with lower silica and high calcium, and then the trend is moving different toward the top, where the content of silica is increasing and the content of calcium is decreasing. And the same happens with the aluminium, like following the, in general, follows the silicium curve. And here we have two detailed examples of how this curve looks like. So if we take the 54 feet on the top, this red box is this one, where we can see a TOC-rich section. And that is really different of what we see at the very top of our core, where is more coarser, representing more sands, and we have probably different facies. So this was more an overview. Okay, so we have done for this preliminary analysis a discrimination between event and background. As we can see, the event are colored with orange and the background is colored by blue. We have done the quantification and we have almost 50-50, but it's like 51 for background and almost 49% of, sorry, 51 for event and 49 for background. And here we can see the histogram regarding the thickness. So in both cases we have up to 3 feet, and we can see that we have a lot of events and backgrounds are less than half a feet, and a few that are up to 2 or 3. What is an interesting point is that even though both represent almost the same thickness, the rate of deposition for those are really different in scale of time. So that was an interesting thing to point it out. Then for the image that is on the right, what we did was we selected only the events and the background packages that are more than 1 feet, because otherwise it would be messy here if we wouldn't understand what is going on. So we selected those as, and so every curve will represent an event, and every curve here would represent a package of background. And they have the same color because this is collecting the data from the same package. So we can see in the silicium box that there is a trend where the vent, that means that the vent would start, as we saw before, with a less content of silica increasing towards the top, while the calcium shows the different trend. And in here we choose the nickel because this is a proxy for redox conditions representing anoxia. So we can see that there is a correlation between also the nickel and the silicium. While in the background, the trend is not that clear. I mean, there is some trend but is more curved, that the composition is changing, going from certain percentage of silica decreasing and then increasing. And the opposite would happen with the calcium. And we have seen this type of behavior where we have an diagenesis there. So we know that we have a overprinting of the diagenesis, and we know that is going to be a challenge. And we are going to show some examples after this. So I selected one portion of the core to show how the event and the background looks like. And we can see again that there are some trends that we can identify. And then I'm going to show here how this is composed. So here we can see part of the vent where we fainted laminated milestones, for instance. Here we have the starting of a new event with a more calcareous towards the base, as I mentioned before. That would end up here, and then we have another background following. Where, like, one thing that we notice from this data set is that when we have these kind of edges and these changes in density, we can link that in general with the diagenesis. And we have seen a really good example of those along the core, where we can see concretions almost capturing the most part of the concretion, and that's what we see. So here we have another comparison. In this case, we have, well, I am not going to dig into the facies, but we have done the facies analysis for these also. We can, at least what we can see is that an event can be conformed by more than one facies, as we can see here. For instance, in this particular case, we have a more coarse grain, like a sand grain size for carbonates, where we have skeletal fragments, as we can see here. This is the bottom of the event, where we have erosive contact, skeletal fragments, and we can see a normal gradient towards the top. And if we go here, we can see what we will call the H3 if we follow the Hutton model, and which would be the hybrid event beds. And if we can see here in the XRF, there are some trends, as I mentioned before, where it starts with a low content of silicium, starting with ended up with a greater content of it, and the calcium would do the opposite. So that is similar in terms of the trends that we will see in the background, where, as we can see here, there are two trends that we can point it out, depending on the scale, obviously, but we can see we have described this as a background that would be composed both for two trends of low content of silicium ended up with a higher content of silicium. So what is important from here is that even though an XRF...
You have 2 minutes
okay.
left. Yeah.
Okay. So if the XRF is useful to guide you to discrimination, it's not going to give you an answer, but it's useful to have CT and XRF all together. So regarding the future work, the main goal is to be able to do a quantification of lateral heterogeneity, to use these two walls, the vertical and the slant. So for that, we want to have XRF data acquisition and to do facies description on the slant wall. Then we want to do the correlation between those walls. And after that, we can define good areas where we want to collect thin sections to do a better job doing a detailed composition and diagenesis analysis. And this is how, just to give an idea how the slant wall looks like and how the vents look like, we can see that we can still split into background and event bed. That's why we believe that we will be able to do a correlation between them. So this is, we haven't done a further analysis in that, it's just to show that we can do this. This is how an event looks like, a background looks like, and then we will obviously do a facies analysis per each event and background package. We can see that the quality of the pictures are really good. That would allow us to do a good job. And we haven't seen the core yet. That's why we are doing this detailed work now. And then we will visit the core and do a more detailed analysis then. And it's, thank you.
Yes, thank you very much. It was a beautiful talk.
Thank you.
I liked it. But what is the age of the Wolfcamp Formation? I missed that.
It is the Pennsylvania. It's in the Permian, the Pennsylvanian.
Ah, the Permian, Pennsylvania.
Yeah.
But what struck me when you were discussing these basin finds, the backgrounds, is that you find a sort of anti-correlation with the calcium and the silica.
Yes.
And
Yes.
Have you any idea how, from thin section analysis, what the grain size is of the silica?
So the thing is that for the silica, we have two sources, like one is biogenic and one would be more like lytics. And we have seen different, like depending on what is the source, we will be able to see, for instance, quartz grain if we have more siliciclastic deposits and more like and that would be different if we have biogenic influx. We cannot tell about that exactly just looking into the pictures. That's why we will select specific areas where we want to do at least 20 thin sections to do a good job trying to discriminate the different sources of the siliceous components, and also trying to do a good job trying to discriminate the diagenesis.
Yeah, it made me think of samples that we took from the Indus-fan in the hemipelagic intervals, where we clearly see dust coming in, and then you get a sort of anti-correlation of more calcium
Yes.
and less silica. And the silica is then fine grade, typically of a size of 20 to 30 micron.
Yeah, like in the background, the most common facies is the siliceous mudstone. So in general, at least in the background, is a really fine deposit. And that is one of the main difference with the vent, where we can see up to, at least for as far we can tell, that we have like sun grain size. So there is a clear difference between the grain size in the background, that is mainly silty mudstone or mudstone,
yeah,
and the vent where we also have like at the top of it mudstone and silty mudstone, but at the base we have a coarser grain, that's for sure.
Okay, thank you very much. We have to move on, Leonela. Thank you for your nice talk.